Welcome to Smart Physics. As we continue our step-by-step walkthrough through the Cambridge IGCSE Physics Paper 4, Component 41 of the October-November 2025 series. In this particular video, we'll zero in on question number 2. So let's quickly delve into it. Question number 2. Table 2.1 contains information about the planet Mars. Mass of Mars 6.4 times 10 to the power 23 kgs. Gravitational field strength at its surface 3.7 newtons per kg. And average density is 3,900 kilograms per cubic meter. Define gravitational field strength. Gravitational field strength is what we normally just refer to as a small g. For us to define gravitational field strength effectively, we should recall that weight is equal to mass times gravitational field strength. Since we want to define gravitational field strength, we need to make gravitational field strength subject to formula. So I'm going to divide both sides by m, and we remain with G is equal to W over m. You should recall that weight is a force, so similarly we can say this is force over m. Now to define gravitational field strength, we navigate from this mathematical formula, G is equal to force divided by mass, and we put this expression in words which says gravitational field strength is the force per unit mass in a gravitational field. So the expected answer was gravitational field strength is the force per unit mass on an object in a gravitational field. With this, you earn your mark. B, item 1. An object has a weight of 42 newtons at the surface of the earth. Calculate the weight of the object at the surface of Mars. Now, this question required students to recall that mass does not change from place to place. Mass is constant irrespective of places. So the mass on Earth is equals to the mass on the surface of Mars. So we needed to use the data provided for the surface of Earth to find the mass on Earth. Once we find the mass on Earth, we use that mass to find the weight on Mars. Now, key things to remember: gravitational field strength on Earth is 9.8 newtons per kg. This you should always know. You are required to know this. In an exam situation, if you happen to forget, what do? You go to the instructions, the cover page, you find it given over there. So let's use the equation for weight, mass, and gravity to find the mass of the object on Earth. We know that weight is mass times gravity. Then we change the subject because we're looking for mass. By changing the subject, we have mass is equal to weight divided by gravity. The next thing is substitution. We know that the weight is 42 and gravity is 9.8. We do substitution for us to find our mass of the object to be 4.29. With this done, we can now recall the equation for weight again. We know that weight is mass times gravity. So where do we get the mass? The mass of an object on Earth is equal to the mass of an object on Mars. So this is the mass we are going to recall here and say, since mass on Earth is equal to mass on Mars, the 4.29 kg is the mass of the object wherever it is. So we do our substitution. 4.29 times gravitational field strength of Mars, which is given on the table as 3.7, and we get our 15.87 newtons. Two important things before you present your final answer in the space provided. If the units are not given here, you are required to put units. So your final answer must have units. Number 1, units. Number 2, our answers should be to a minimum of 2 significant figures in our presentation. So the ideal answer will be 16 newtons. A minimum of 2 significant figures with units. If any of these is wrong, then the answer, you cannot get the answer mark. Part 2 of B, calculate the volume of mass. For us to find the volume, we need to recall the equation for mass, density, and volume. And let's extract data and see what we were given in the table. So in the table, we are given the mass of Mars and we are given the density of mass. With this, we should know that density is mass per unit volume, which is mass divided by volume. We are looking for volume. Let's change the subject. We are going to say volume is mass divided by density. Straight substitution, and we find 1.6 times 10 to the power 20 cubic meters. Don't forget always these two rules. Units, if not given, my unit is there. A minimum of 2 significant figures. A minimum of 2 significant figures. With this, you earn all the marks. Part C reads, Fig 2.1 shows a space buggy that is tested on Earth. So the experiment is happening on Earth. The buggy is traveling at a constant speed in a straight line. This is very important information. If you like highlighting, this part should be the one you highlight. It's very important because speed in a straight line is velocity. Speed in a straight line is velocity. In other words, we can actually say it's moving at a constant velocity. The driving force is 30 newtons. So the driving force is 30 newtons. Item 1. Draw and label one arrow on Fig 2.1 to show the size and direction of the resistive forces on the buggy. Now, since they said it's traveling at a constant speed in a straight line, velocity is constant. And if velocity is constant, acceleration is 0. Velocity is constant. If velocity is constant, acceleration is 0. Because acceleration is the rate of change of velocity. Since velocity is constant, the velocity is not changing. So the rate of change of velocity is 0, meaning acceleration is 0. And according to Newton's second law, if acceleration is 0, the net force is also 0. And if the net force is 0, the driving force and the resistive forces are balanced. In other words, the force going backwards is also 30 newtons. So that if we say 30 driving force minus 30 opposing force, we're going to get a net force of 0, which gives us an acceleration of 0. Hence, we say the object is in dynamic equilibrium. Dynamic equilibrium. It's moving, but it's at equilibrium. It's in dynamic equilibrium. The resistive force balances the driving force, meaning it will maintain the same velocity since there is no acceleration. With this, that's how you earn your 2 marks. Direction and magnitude. Direction is opposing, magnitude is equal. How do we know there is no acceleration? How do we know velocity is constant? Therefore, there is no net force. Part 2 of C. Air resistance on Mars is less than air resistance on Earth. The same driving force is exerted on the buggy on Mars. State the effect this has on the resultant force on the buggy on Mars. Let me draw something here to illustrate what's happening. So I'll start with the situation on Earth. On Earth, this is on Earth, the buggy is under the influence of a driving force of 30 newtons. And we said the resistive force is also 30 newtons. So that F net is equals to 30 newtons minus 30 newtons, which is equal to 0. Now, let's go to Mars. We expose it to the same driving force of 30 newtons, but the air resistance becomes less, meaning the opposing force is less. For argument's sake, I'm going to say it's 20 newtons, for argument's sake. So what will be the net force in this particular case? So the net force will be 30 newtons driving force minus 20 newtons opposing force to give us 10 newtons. So on Earth, the net force is 0. On Mars, the net force is bigger than 0. So the net force on Mars is greater than the net force on Earth. In other words, we can actually say the effect causes the net force or the resultant force to increase. So the ideal answer was the resultant force increases or it becomes greater. State the relationship between the resistive forces, driving forces, and opposing forces. Since they are opposing each other, we are going to allocate one positive, one negative. Therefore, the resultant force is equal to driving force minus resistive force. This is the particular relationship. I hope you have enjoyed today's class and you have received fundamental helps on the principles on question number 2. See you in the next video when I'm dismantling question number 3.